distance. So what we have in our notations, we've just like written it here. So the potential falls like 1 over r squared, which means the force is going to go like 1 over r cubed. And then in the case of the 2-point charges, you see the dipole moment here. This is the so-called dipole moment. If my density of charges was just 2 delta functions with a distance like this, this would just be the charge times the distance between the two. Okay, so what would that mean? So let me choose an axis for coordinates along the dipole like this. So let's put our axis like this for spherical coordinates. Along the dipole. And what that means is that our phi dipole of position r just becomes this 1 over 4 pi epsilon 0. Just rewriting this now with that thing. The p is along the z-axis. But now I just have this p cos theta divided by r squared. Okay, p is q times d, and that's the charge, and that's the distance with the dipole, but I take d to infinity. So that's the dipole moment that I have here. It's a given number, right? Now, what I know is that the electrical field is minus grad of phi. Okay, and here I'm going to use spherical coordinates. Essentially, I want to have the gradient in spherical coordinates, which is in the notes. So yeah, so the gradient of a certain function phi in spherical coordinates looks like this. So I've got the d phi dr in the r hat direction. I've got 1 over r d phi d theta in the theta hat direction, and I've got the 1 over r sine theta d phi d the azimuthal angle in the phi hat direction. Okay, so here what that means is that the r component of the electrical field is just going to be the r derivative of that thing. So it's minus 1 over r. Yeah, so I mean, let's do it straight, right? So I have to take the r derivative of this and put a minus sign. I've got r to the power of minus 2. So then I pick up a minus 2, but then there's a minus sign, so it's a plus 2. So so this thing is just minus d phi dr, which is equal to 1 over 4 pi epsilon 0. And now I have just a p, the factor of 2 p cos theta divided by r cubed. So that's the first component that we have. The e in the theta direction. So this one is just minus 1 over r and p theta, minus 1 over r d theta of the phi that we have. So here I just take the derivative of cos theta, which gives me minus sign. So I've got a plus here because of that. So here I get 1 over 4 pi epsilon 0. And here I just get p sine theta divided by r cubed. And the other components along the azimuthal angle phi. This is, again, just the derivative here, but there's no dependence on the phi, so this one is 0. There's nobody there. So how does this look? If you look at the field, I have my little dipole moment like this, pqed in this direction. The field of that thing, I tried to draw it before. You'll find some marvelous illustrations in Purcell-Morin. Maybe I can try to do it well. So you have outgoing field lines like this, incoming field lines like this. But as you go out, the field lines turn around, and they become more and more intense. Yeah, so you have lots of field lines like this. Okay, so and then they weaken as you go out like this. Okay, so the R value, so in these notations, right, ER is the one as I move away from my origin, so ER would be along the radial part here, and the E theta is the one going as I increase the angle theta in this system of coordinates, so as I come down here. So that's the idea. So it starts strong in the positive direction when theta is like 0, but when theta becomes like pi over 2, the radial part just goes to 0, but the theta part becomes very, very strong. So if you have positive negative charge like this, the electrical field on the plane here is actually pointing down, pointing up as you're here, but then it weakens and changes until it starts pointing down here. So it's very, very different from the field of single charge, right, which is always purely radial. The dipole field depends on where you're looking at it. So if you have a certain charge, you've got the dipole like this, positive, negative, the charge is actually going to be pulled down. Okay? So that's the way you kind of, I invite you to look at the book of Purcell-Morin, because they've really got these wonderful illustrations of these dipole fields, how they come out. Okay, but that's how you kind of calculate this, this thing. In the notes, there are kind of equivalent expressions for all these things, but I'm not going to insist on this. You can just look at it, and there are lots of fun problems to be done with dipoles like this, so it's worth playing with this a little bit. Okay. Am I correct that you've drawn this field of dipoles before in your first course? It's nothing magical. It's really just combinations of Coulomb's law itself. Okay, but it's good to kind of familiarize yourself with it. Maybe as a final comment, just how do you understand the different moments coming one after the other? I think it's pretty clear what the monopole term is, right? It's the average of all the charges that you have. Any residual non-zero value after you sum all the charges together gives you the monopole term. The dipole, we've seen, it looks like any effect that remains when you've got distributions of charges that are spatially split from each other, like this. So this configuration here would have a 0 monopole term, but a non-zero dipole term. Okay? Now, conversely, when you start looking at higher and higher moments, you can think of configurations that have also 0 monopole and 0 dipole, but non-zero quadrupole moments. So for example, here, if I start with a dipole here plus minus, but then I put the converse dipole here on the other side, minus plus. So these two dipole moments, one pointing up, one pointing down, they kind of cancel. So if I look at this from very, very far away, the potential coming from that object will have a 0 monopole term, a 0 dipole term, but a non-zero quadrupole term. Okay, so maybe in some circumstances in your life, you'll end up with configurations like that do that. Yeah. By the way, you know, gravitational waves, they're quadrupolar. Yeah, so there's no dipole wave. But that's easy. Okay, so yeah, I guess that's what I wanted to say about these things. We'll get back to the multipole expansion when we've talked about magnetic fields and whatnot. The thing I do want you to remember is that all our discussion for the multipole expansion is purely based on some mathematical considerations of the 1 over r function. Okay, so it's, anytime you see this 1 over r, everything we've said about this is going to be applicable to that. Okay? So yes, question. So all these potentials here, you can verify that, so we're still doing like electrostatics. So for all these potentials, you can verify that the curl of the electrical field that you come in here will be 0. So if you do any like line integral of the field derived from that thing, it will be 0, because this potential is still derived from, this field is still derived from the gradient of the potential, which is single value. And that's essentially the only condition that you need, because the curl of the gradient is mathematically 0. Then when I write down my multipole expansion, I still write a single value function in space whose gradient gives me the field. And the very fact that this field is a gradient guarantees for you, without any negotiation possibility, that the curl of the field that you obtain will be 0. So that still absolutely holds. Okay, but once again, I remind you, this is a statement which is limited to the electrostatic case. When we start moving things around dynamically, this will not hold true anymore. But we're not there yet. Yeah? Other question?
Maybe this makes sense something classic math, but I don't know if what for what use the multiple potentials and what its difference is from this calculating the potential from superposition principle.
Okay. So the question is, what use is this? Essentially, the use of this is really to simplify your life considerably. Because if I was to give you a complicated distribution of charges, or perhaps we're doing like atomic physics and we're looking at, we're looking at a water molecule. So I've got water molecule like that, and I've got charges distributed in here, and I can approximate, of course, quantum mechanically, this is very complicated what happens with this, because the electrons are like flying around all over the place, but there is a charge imbalance between these. And the charge imbalance leads to a measurable electrostatic potential coming from such objects. The total charge is 0, so it has no monopole term. But the dipole term of such an object is non-zero. So you see, if I have a little molecule like that, I would simplify my life by saying, let me compute its dipole moment. And then I compute that once and for all. Because quantum mechanically, I know the angle that I've got here. I can do the integral of the wave functions for the electrons and whatnot. And I compute a number once in my life, which is the dipole moment of the water molecule. And I do that for whatever other molecule that I have. I can do the quadrupole moment for these things as well. And once I have done this once in my life, I can use it absolutely everywhere, all the time. And then if you give me a configuration of lots of different water molecules, blah, 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 what do? I just essentially take it piece by piece. Each one I approximate with the dipole potential coming from that thing, sum it up, and that's the potential that you have. So it's a way of greatly simplifying your general problems into little pieces that you can file up and, you know.
Does it help you that it's possible to have
yeah.
Does it just take all of the charges? Do a lot of extra work?
Yes, you do. You save yourself a lot of extra work when you properly understand that for particular configurations, you can compute these moments once and for all, and then you know them. Okay, so that's the use where this is done. Later, when we'll talk about electrostatics and magnetostatics in matter, we'll reuse those concepts a little bit. But for now, it's really meant as an ultra handy and very accurate approximation scheme that exploits the fact that there's a huge separation in the spatial dependence depending on the particular moment that you're considering here. So that's what really helps you. So for all practical matters, you can get away with things. I mean, most of the things that you are confronted with, they're just physics of dipoles. Very rarely do you get physics of quadrupoles. And for the rest, you know, almost never. So that's the idea. Okay. So yeah, in the notes there are lots of things about you know, quadrupoles, higher moments, but just forget about all of that. Okay. So let's see. I was planning to have this done after the first hour. It's a bit late, but let's see how we do. I would now like to move on to the question.
How would the dipole put that?
So here, the dipole itself has up-down vertical in this drawing here. Okay, so that's why you see there's a stronger up arrow here, because when you're coming from this axis, you're slightly closer to the positive charge. And conversely, down here, the field is the other way because, you know, you're attracted. But it falls off. I mean, the field falls off like 1 over r cubed. That's the point, right? So not 1 over r squared. It's now 1 over r cubed. That's the thing. So these are weak fields as compared to the fields that you would get from a single isolated charge. Yeah, but nonetheless, like most matter is electrically neutral. So very often the kind of contact point that you have with a piece of matter is through dipole effects like this. And then there are lots of fun examples in Purcell-Morin, also about the physics of these dipoles, talking indeed about like you know, geckos walking on ceilings, and you know how much weight you could actually put on a gecko if that's so. These are incredibly I mean, in a sense, they're weak forces as compared to the monopole terms, but atoms are so small, and these things add up so much, but these are humongous forces in the end. So please have a look at these fun examples in Purcell-Morin, because they really they make good fun with this. And of course, if you do, once again, quantum mechanics, if you're doing a lot of atomic physics, then most of the times the interactions you're interested in are these dipole-dipole interactions. And then you take the molecules, you compute their moments once and for all, and then you can write down all your Hamiltonians, do all your fun stuff with that. Okay? So that's it.